Well, thank you very much, Mariette, and hello everybody. Thank you for joining for this session today and giving me this opportunity to speak to you. I'll just say a few words about myself. I work for Tata Steel in particular. I'm a structures engineer with the structural hollow section division, which is amongst many Tata Steel manufacturing product divisions, not just in construction. My background is a structural engineer. I've worked in steel construction all of my working life as a design engineer, as a proposals manager, estimating, business development. So my full background's steel construction. And what I'm going to talk about today, it's a UK focused, I suppose, but it is valid elsewhere, and general steel making, sustainability, and how to get to net zero. And then the use of structural little sections due to their efficiency can be a tool that structural engineers can use to accommodate efficient design. So I'll just go through the slide pack and I look forward to some questions at the end. So these are basically the headings: sustainability, the challenges and responses, life cycle perspective, whole life carbon, transparency and reporting, different steel making routes, how to get to net zero, and then embodied carbon factors. That will be based around the IStructE publication, which has been issued in the last 18 months or so. And then I'll talk about efficient use of structural hollow sections in design. So this topic's quite current with COP28 starting in Dubai today. It should be underway by now with the time difference. So I'll just get going. So a number of years ago, the UN published these sustainability development goals, which are all very noble and goals worth pursuing. It's to do with poverty, clean water, freedom of speech. So all good causes, and in particular, climate change. It's surely happening. We're experiencing it in the UK, lots of rain and unseasonably cold, the coldest way below average temperatures the last few days. Promoting the circular economy, what we use, what happens to it, and then being responsible as a business, as Tata Steel, but also socially and as an individual, being responsible in the way that you consume products and how you dispose of them. So those challenges are responded to by Tata Steel. In our sustainability report, we reference those 17 goals in our reporting. So climate change, to minimize the change, changing the way that we manufacture steel. It's been in development for a number of years now. We have made a lot of progress, but lots of things are being looked at and have been looked at. For instance, there's carbon capture storage, and also using that stored carbon to utilize it to make other useful products. So we've been active in developing schemes for that and moving forward into. And then we also promote the circular economy, what you do with how you use resources to make something, and then how you dispose of it. And within Tata Steel, we have this carbon assessment, life cycle assessment capability in-house. And we also publish a lot of data in a transparent manner, annual reporting through our EPD. We operate our own schemes. We publish over 100 EPDs for our product chain. So this little cheeky image is just to demonstrate that looking at something in isolation may not be the best solution. This is demonstrating a fossil fuel vehicle, a diesel vehicle. It has emissions, definitely. An electric vehicle, no emissions when you're operating it, but if you look at the life cycle, electric vehicle, it doesn't operate without the electricity to charge the batteries to operate the vehicle, and that can come from a multitude of power sources depending on which part of the world. The UK is a mix of energy. Other countries are much less so, like coal powered or oil fired power generation. That's contributing to carbon emissions. But I'm not promoting a diesel vehicle. It's just emissions happen, and how you collate them. That's the reason why you have EPDs that should cover the full life cycle of a product. So the life cycle stages, you can obviously just hone in the beginning, the A1 to A3, the upfront carbon. If you're constructing a building, products go into it. Steel is one of them. So Tata Steel make iron, make steel, and then we transform the steel into products for use in buildings. So that's the A1 to A3 module stages. So that's your upfront carbon. And then when you go onto the site, module A4 and A5, then that's the construction process. A building has a life, and that will add to carbon emissions during the lifetime of that building. The HVAC, the air conditioning, what the water is used, what maintenance required, what you have to replace things. So that's the embodied carbon stage. That's the term, the operational carbon. For instance, structural engineers will not look at the operational carbon. That's a different discipline. Structural engineers can look at, in particular, the module A1 to A3, the scope 1 and 2 emissions. Scope 3 emissions is the construction process. And then the end of life, how you demolish a structure, what happens to it? Do you have transport it somewhere else? How do you dispose of the waste? So that's a cradle to grave approach to carbon assessment. You use something, you build something, you use it, and then you dispose of it. The whole life carbon is when you start to look at the data associated with module D. So that's, can you reuse something? Steel is a very reusable material. In the UK, there are case studies of where a developer has had a steel frame building. He's demolished the building, he's recovered the steel and used it in another project. You can recycle material. Some materials are more recyclable than other, and some have no recycling benefit. They go to landfill. So that's a big downside in some materials. That's whole life carbon. So that's a circular economy approach. Use something, and can you put it back into the circular economy to be reused as something else? So this is a case study from a couple of years ago, looking at different roofing systems, steel roofs, bitumen roof, concrete tiled roof. So if you look at the histogram, that shows the total life cycle of that particular system. So you'll see that the construction phase, you'll see the bitumen has much less carbon associated with it, as opposed to the concrete and the steel, which obviously have much higher uh, carbon emissions associated with it due to their manufacturing. But if you consider the full life cycle, the operational side, the the bitumen roof requires a lot more maintenance. It's not as, it hasn't the same design life as the other products in the roofing system. And then if you look at the end of life, uh, the the you'll see that it's much higher carbon associated with it. So it's much higher circular economy carbon calculation using a bitumen roof over the other materials. The steel comes out better because it is 100% recyclable. So it has a positive effect on the overall carbon emissions. So using things now, what happens in the future? How do things get disposed of? And this is just talking about plastic containers, which are very popular. And they are a good product for a number of reasons in operation, because they're inexpensive, they're hygienic, and convenient. At the end of life, you've used it, you throw it away, but the consequence of that is that all of this plastic is shipped around the world, potentially with no place to go. So, although a good product, the full life cycle hasn't been thought through. And this concept was actually part of a report, the Brundtland report, actually issued in 1987. So that demonstrates how long sustainability has been an issue being talked about moving forward. We're getting closer to 2030 and the 1.5 degree increase in global temperatures. So regarding steel, it is fundamental for the transition to greener energy, whichever mode of energy generation you're looking at, there will be steel involved in it. Steel will be involved in all processes, everything from making products, for making buildings. Steel will be involved in that, even just the machinery for undertaking the manufacture. So steel will be required as an ongoing material. So this is one of my sustainability colleagues having some refurbishment done. And you'll see various construction materials get put into a rubbish skip for disposal. And you'll notice some of the materials that you would expect: concrete, wood, steel, cast iron. So that's what the image on the left shows, what was in the skip, but some of the materials disappear because of all the steel materials get recycled. So somebody will come and collect steel materials from your doorstep. If you have a cooker or refrigerator you're finished with in the UK, if you put it on your driveway, then somebody will come and collect it uh, for recycling, because it has an intrinsic value, because scrap material is a global commodity. So information. Assessing sustainability credentials, you need information, but you have to be aware of how transparent it is and how relevant, because not everything is as it seems in first report. So we operate our own EPD schemes. We're the only steel company that does that. We do have it third-party verified. We use a verification body to ensure our processes comply with the correct standards. So with green certification schemes, we have certification that demonstrate that our products are sourced responsibly. So that responsible sourcing covers all of our processes, from raw material extraction, making the iron, making the steel, transforming the steel into other products. So that covers our full construction portfolio, and that can give you points under those certification schemes. So the information that Tata Steel disclose, we work with World Steel, various bodies. We produce an annual report. All of the information that Tata Steel produce is available free of charge via our website, or contacting somebody like myself, and we will give you any assistance you require for getting that data you required. So we look at the EU emissions scheme. We have to take it part of that. That's a legal requirement. Benchmarking against World Steel, best practice. We disclose all of our carbon emissions. We pre-qualify our materials with different end users. We have our environmental product declaration and our sustainability report, which is published every year. So Tata Steel have a number of large sites in the UK, and so we do, as part of our uh, social values sort of thing, we do have some like nature reserves in some of our facilities. One of which is one of our plants in Shotton in North Wales. So there's that land that's owned that is maintained as a bird sanctuary. So we basically maintain making sure the environment's good for the sort of birds that use this sort of environment. And it's not a closed place; it's open to the public to visit. As a so some developers and end users think that you can, if you specify the way that you make steel, then that is that's reducing carbon. But on the surface, that may look the case, but when you look at the figures, it's not actually as clear cut as that because they are interrelated to a certain extent. So two fundamental ways of making iron or steel, ultimately. A blast furnace is used to make iron, and that gets transformed into steel. An electric arc furnace doesn't actually make steel. It basically takes scrap material and makes other steel that can be used for other applications. So different types of steel processes to make products, ultimately. So a blast furnace, primary steel making, takes iron ore, coal generally from the to make to break to basically make the iron, releasing a lot of carbon dioxide, and then goes into making steel. Electric arc furnace is called secondary because you're not actually making new steel. A blast furnace makes virgin steel. Electric furnace is making secondary steel. It's repurposing steel. A blast furnace does use recycled content. You can make lots of different types of steel. With an electric arc furnace, more care is required to make sure, because obviously different scrap that goes into an electric furnace has a big influence on the steel that gets produced using the process. So the blast furnace makes the feedstock for an electric arc furnace. Without the blast furnace, the electric arc furnace wouldn't exist. So embodied carbon factors. So you make steel, fresh steel goes into construction, structural engineering. Structures are finished with. The steel gets reused, or the supply chain for recycling is very good because steel has a value, and it goes into making via steel using electric arc furnace steel making route up to 100% scrap, and then up to 25% goes back into primary steel making. So currently around 40% of steel comes from the electric arc furnace steel making route. Obviously that's not sufficient to satisfy global demand. So the current steel demand is around 2 billion tons of steel per annum. So only 800,000 tons can be achieved using electric arc furnace routes. So they are interlinked. So if there would be no blast furnaces, then there'd be insufficient steel supply to satisfy demand, which obviously would have a huge effect on the global economy. So steel production requirements will be increasing until at least 2050, because obviously developing countries want steel products, as do the developed countries. They'll still want what they require through cars, construction, packaging. So steel demand is not static. It will increase, not a great amount next few years forecast, but that will, as the world economy recovers, increase the requirement for steel production. a lot of countries are increasing their steel production. So steel making in the UK, it's predominantly Tata Steel and British Steel. The one that Tata Steel operate in South Wales is the biggest in the UK. So that takes iron ore and coking coal to make iron, and then made into steel coils for downstream operations in various sectors. So there's two blast furnaces there, and it's the biggest CO2 emitter in the UK, around 6 million tonnes per annum of carbon emissions, making around 3 million tonnes of steel. So these are the processes that the current asset setup is. So it takes raw materials, makes coke from coal, sinter, the iron sorting into the blast furnace with the iron ore, then steel making, casting, hot rolling. All of Tata Steel's products start as a rolled coil. We make hollow sections from coil. We make decking from coil. We make cans from coil. So everything that Tata Steel produce in the UK is made from a steel coil. So with regard to neutral steel making, Tata Steel have this pathway called Optimus. It stands for Zero Port Talbot Emissions, and it's basically the roadmap to net zero that Tata Steel are committed to. So the program is to become carbon neutral by 2045, which is 5 years earlier than was initially being planned. So we brought things forward, and we're also looking at reducing our CO2 emissions by 80% by 2035. With our current plans, that is on track. So making steel is a very energy intensive process, but from a cost perspective and also sustainability perspective, we've reduced dramatically the amount of energy required to make a ton of steel. The steel industry far outperforms all other sectors in energy efficiency, and also Tata Steel, we make our steel in an efficient manner. One fundamental commitment is to adopt science-based targets for our operations. Science-based targets are important in that you have to demonstrate that what you're proposing can be done using science. One example of what you can't use for reducing your carbon footprint is using offsetting of future carbon savings, such as using forestry for reducing embodied carbon in your future operations, because embodied carbon in forestry, although the trees store carbon, there is no guarantee of that saving. You're basically forecasting a saving that may or may not happen. So the transparency, lots of information available. If you're looking at EPDs, make sure you're comparing apple for apple, because there's different ways of approaching your EPD, your carbon calculations. It's not just carbon that's reported in EPD. There's all sorts of information there, and all operations regarding the processes that are undertaken. So you see the amount of data that's involved in an EPD. So that encompasses our full process from raw materials through to being delivered to the customer. So a lot of information there. So with regard to structural hollow sections, we make different types of structural hollow section, and this is the figures for our Celsius, that's our hot finished hollow section. So our upfront A1 to A3 carbon carbon figures are 2.81 kilograms per of equivalent of carbon per kilogram of steel. But if you incorporate module D, that's the recycling benefit you get from the steel after end of life. You see it's a big negative, so that reduces the overall carbon effect of that particular product. So what this diagram illustrates is that the blue arrow, that's showing the CO2 associated with making steel. A lot of people bandy around the terms sustainable steel, green steel. It doesn't really tell you anything, that description. It's all to do with the amount of carbon associated with the steel making process. So we're in the sort of pre-transition phase, moving into our transition. So we'll be reporting data to responsible steel using science-based targets, moving into the transition. And also the amount of recycled content will have a bearing on this CO2 reduction program. But if you look at the blue bars at the bottom under the chart, we can only control what we can, energy efficiency, what processes we use, the amount of scrap we use, how do we transform our steel making. All of the other green bars, that's to do with things that are outside of an industry's control. It's what government they can do to facilitate that transition. Where is the green energy going to come from? Without green energy, then the transition can't happen. So that's the big drive to facilitate green energy. Carbon capture storage, that needs infrastructure. Where do you get, if you want to use hydrogen, hydrogen can be used in making steel, for making virgin steel. But where does the hydrogen come from? The infrastructure is not available for producing hydrogen in a sustainable way, and it's also prohibitively expensive in making hydrogen for energy and steel making. So fundamentally, there's two routes that were on the agenda. Transitioning from our current blast furnace manufacturing processes using raw materials to utilizing a smarter carbon usage, still using blast furnaces, introducing hydrogen, carbon capture usage, or do you go for carbon direct avoidance, use electric arc furnace using scrap and using iron made using a smart carbon method to make steel for use in their products. So it's two options really. So in the interim, Tata Steel have introduced this certificate-based solution called Carbon Light. So this program means that you can reduce your carbon intensity through the carbon savings that have been made outside of our EPD. EPDs are produced every 5 years. Our last one was produced in 2022 from data in 2021. So that's in our current EPD. But subsequent to that, we made carbon savings through our processes, and those savings can be banked to be issued to end users to reduce the carbon footprint on on their project or product. So the way it works is, prior to transitioning, the amount of steel product of embodied steel, of low carbon embodied steel, there isn't very much available, but that will become more available after the transition. So if you look at the white bar, that is what customers are looking for now. They're looking for lower carbon intensity steel over that is available from the usual supply chain. So this carbon light certificate is to close the gap between what customers are looking for, and society is looking for, with carbon savings associated with that particular steel product. So the way that the scheme works is, we've reduced carbon through our investment into various schemes, energy, electrification, changing our processes. So that's enabled carbon savings to be accumulated, and they're put into like a bank of carbon savings. We verify those savings through an external verification process utilizing DNV, the Norwegian certification body, who are the world leaders in this sort of scheme. It's not just applicable to steel, it can be used in other high emitting industries as well, to map their global savings and pass that on to end users. So there's carbon certificates can be associated with the steel products that we sell, and our commitment is that the revenue from those sales will go back into process changes to further reduce our carbon emissions. So that's showing the cycle of revenue, decarbonisation, processes implemented, carbon savings, and certification. That gives the customer some carbon intensity savings to pass on. So this is a fundamental difference between this sort of process in reporting carbon savings. It's an insetting scheme. It's a mass allocation of carbon savings. Okay, so you'll see that the operations get greener due to this reinvestment of this carbon light revenue, as opposed to offsetting, where you have a process, a plant emitting carbon, you pay money for certification to try and avoid carbon sequestration in the future. So that's offsetting, insetting, a subtle difference, no big difference actually. So just as an example of one investment that was made to save carbon, this is a £37 million turbo generator, turbocharger, and that turbocharger basically takes our waste gases and generates electricity, which takes electricity away from the UK electricity grid. So that's saving 60,000 tonnes of carbon per annum using that turbo generator. But out of 3 million, that isn't a lot, but it can be associated with a lot of steel as an end user. If you think the plant's currently emitting 3 million tonnes of carbon, so that would have very little impact on an environmental product declaration. That's why it's outside the EPD to associate with some of our products for people that want to pay a premium for having less carbon intensive steel. So there's no current standard as such for this process. So we've used some global protocols to report it, using World Steel as established our emission intensity to determine our CO2 bank for passing on to customers. So repeating DNV, verify that the processes calculating it are as they should be. So it gives you CO2 density reduction now rather than waiting for the transition to give those savings. So that's just showing the same cycle, the certificate offering the savings. So that's a sample certificate. So carbon light, if you were to associate it with a hollow section, so you can choose the amount of carbon reduction you want to be associated. So different percentages give you different global warming potential reduction. So that's Carbon Light and the Optimus program. So this embodied carbon factors we mentioned before. Sustainability is what you do now affects tomorrow, and reducing carbon is part of the sustainability. It's not the only measure of sustainability. Biodiversity is another one, although it's difficult to calculate. But what are you doing to the environment? How can you keep biodiversity in sustainable schemes? So this IStructE document basically has figures for the upfront carbon of a construction material. So it has basically the global warming potential quantity of that material. But does it consider the full life cycle? Steel, as demonstrated, will be recycled because of its intrinsic value. So within the IStructE publication, there's with steel, it has hollow section, closed section. That's the Tata Steel figure. It's figures for plate. It has a figure for UK rolled open sections, which is a figure for a consumption average. So that's a snapshot in time of what open section users data to determine what the value is. So it's an average figure, UK, global, European. So it's an average figure. So that will change over time, depending on the mix of material. So the IStructE guidance now recognises that primary steel making via blast furnace is steel that can be reused, and hence for the full life cycle, Module D is very important for understanding and calculating the overall embodied carbon value for that material. So there's two tables. Table 2.3, that's the cradle to gate, make something, deliver to the customer, that's your upfront carbon. And then Module D, you can reuse, that's obviously the most efficient use of material from a carbon perspective. And then recycling values for steel, that's demonstrated in table 2.9, not just for steel, but for all structural building materials. So steel will be a negative, other materials will be adding to the carbon value. So that's the figures, the table 2.3 and 2.9. But surprising, I mentioned that earlier that the process used for making steel doesn't actually differentiate hugely in the different types of steel making processes that you use when you incorporate take the upfront carbon, but you use module D, which gives a negative, you'll see that whatever source of steel manufacture, the actual total is not greatly different depending on where the steel comes from, because not all steel is made EF. There's figures that an average uh, of only 4 EU steel makers is the figure that's there. So steel could come from elsewhere, the worldwide average, but you'll see there's not a huge difference in the overall figure. So with regard to hollow section, the 2.5 is an average figure. Let's say we make cold formed and hot finished. So the hot finished is more than the cold formed. So that gives a net 1 kilogram of CO2 per ton of steel product, hollow section. So summarizing, true circular economy gives you the true sustainable impact of material. That's module A and D. Boss making, steel making, and EF, similar carbon footprint. So this is from the International Energy Authority, and it's looking at inputs now and inputs in the future. And so some of these will fall away, like technology in 40 years' time will not be as important. That transition will have been made. But the one thing that stays about the same, 43% now and 40% envisaged in the future, and that's material efficiency. So basically that means that's making it incumbent on designers to use less in their designs, be efficient in what you're designing. So high utilization factors of material, but still safe. And hollow section, with smart lean design, you can make steel weight savings, particularly in compression. Hollow section is very efficient. We make lots of different products, a wide range of sizes. We manufacture in high strength steel, and there's some other benefits as well that may not be as readily known. So you can use a lighter section for the same load capacity. So that's really it for me today. If there's any questions, I'll do my best to answer them.